So I'm recording it right now. I'm going to also show you a video so you can have a better picture how the experiment is done. Okay, so the first hour is going to be some of the theory. Okay, and then the remaining 2 hours is going to be the so-called lab. And yes, so there is some closed captioning going on here. Okay, let's see if it's good, if they do a good job. Hopefully it will show up in our recording. And here is the one of the videos that we have right out there, but let me also show you. Okay, right in here, the Canvas, right? Canvas page. I just want to show you what we have. I have the version number 3 syllabus. I have to make some minor adjustments to the syllabus. And for the schedule, right? And don't forget, I have the notes for 2024. Here are the notes for 2023 year. We have the new videos for 2024 and the old videos for 2023. Don't forget, those are the old versions for old notes for 2023. Let's see. The last class meeting was on the 14th, which was a week ago. Let's see if it's posted already. Right? Here you go. Yeah, here you go. Here are the videos for 2023 for the course. Okay, so we do have the videos for 2020. We do have the videos posted of the last class meeting. Okay. Going back to home page. Yep. More students coming in. Electric charges. Okay, so here you go. Let me give you a little bit of a heads up on the electric potential. I told you how electric potential works, right? And I'm gonna cover here my notes. More students coming. Yeah, 3 people, huh? I'm waiting. Let's see. Here you go. More the merrier. Let me take this one out of my notes. Okay, Wednesday. Okay, so what I didn't cover yet was equipotentials. Equipotentials, okay? And this idea of equipotentials is used in the experiment, the so-called experiment that we are doing, okay? We are doing. And let me give you an illustration how equipotentials go. And one more thing, right? Before we talk about the equipotentials, let me tell you something else, okay? The idea of potential is used in the same way that we use conservation of energy in mechanics. Okay, so since electric potential is related to electric potential energy, EPE, okay, we can now use conservation of energy to determine for instance, the velocity of a given electric charge, okay? And again, make an example, but I'm gonna go do a quick example here for you so you have an idea how we can use this idea of electric potential, right? Okay, so consider, for instance, an electric charge subjected to a uniform electric subjected not to the uniform, subjected to an electric potential. Okay, electrical potential V, an electric charge of charge Q, an electric charge of charge Q at rest, okay, subjected to an electric potential V. Okay. So I'm going to give you a very nice example. Let's see if I can get one here in my slides so you can. Okay, right in here, right? Let's see this one here. Okay. No, not this one. Let's see. Okay, consider this one here. This, what you see right here, is very analogous to this situation here of the mass on the Earth, nearby the Earth's surface, right? You have a mass here on the surface of the Earth. You raise it against the gravitational field, and if you release it, this mass is going to move downwards, right? It's going to be attracted towards the Earth. What you have right here on the left side, the analogous of that for the electric counterpart of the mechanical one, is this one here on the right. Okay, but the difference is that we must have an electric charge, a negative electric charge, and an electric charge that's positive. Okay, so these two charges, they tend to attract each other. So when I raise this positive charge away from the negative charge, what's going to happen? This positive charge is going to gain electric potential energy. Once I release this electric charge, she's going to move towards the larger charge, okay? And the solution of this problem is very similar to the solution of this problem that you see right here. Okay, suppose that we know the potential, the electric potential of this charge at this position, right? V, and it's initially at rest. Okay, what is that going to be the potential? What's going to be the velocity of this charge at a given distance from the main charge? Okay, so what you have to do here is just to use the conservation of energy. Just use, well, conservation of energy. Okay, and it's gonna be like that. Electric potential energy, initial electrical potential energy. We usually call it U for the electric potential energy. Plus initial kinetic energy. Let's see, better, okay, must be equal to final potential energy plus final kinetic energy. And we do that, why we can do that? We can do that because, okay, we do have conservation of energy because the electric potential energy because the electric force, not the electric potential energy, but the electric force is a conservative force. Conservative force. Assume, okay, assume, and then I'm gonna put here, assume there is no friction, right? Assume there is no loss of energy. Okay. Okay, and now that's gonna be the, let's see. Consider, for instance, an electric charge of charge Q at rest subject to initial electric potential. Let's put it this way, to initial electric potential V naught. Just better this way. Just better this way. Okay. Assume there is no loss of energy at rest, initial at rest. Okay. What is the final velocity of this charge? At a point where the final potential is VF. Is VF. Like that. This is a very good. Consider, for instance, an electric charge of charge Q and mass M. I gotta put it here, mass M as well. At rest, example. I'm gonna give an example, right? Example of electric potential and electric potential energy. Okay, consider an electric charge of charge Q and mass M at rest, subjected to an initial electric potential V naught. What is it going to be its final velocity? The final velocity of this charge at a point where its final potential is VF, right? Assuming that there is no loss of, assume that energy is conserved, assume that energy is conserved. That energy is conserved, better. That energy is conserved. Okay. So the solution. Just use conservation of energy. Okay. We do have conservation of energy because the electric force is conservative. I'm sharing my screen, right, with you? Just confirm that with me, please.
Yes, you are, Professor.
Okay, thank you. Okay, so here you go. We have initial potential, we have final potential, and the initial potential just going to be the charge Q multiplied by the electric potential V, which is given, by the way. Remember? Electric potential is defined as the electric potential energy divided by the charge. Initial kinetic energy is going to be 0 because the charge is initially at rest. The final potential energy is going to be QVF. And the final kinetic energy is going to be half mv squared. Like that. M is given, Q is given, V naught and VF are given. Okay, so for this specific situation that you have here, so what is that going to be? I'm going to copy and paste. Okay, so here you go. The situation is going to be somewhat like that. Not only you have a charge Q, but also at this spot, the charge Q will have an electric potential V naught. Okay. Subscript. And then at this point right here at the bottom, just before it strikes the big charge, okay, just before it strikes the big charge, the electric potential is going to be VF. Okay. That's how we do this problem. That's how we illustrate this problem. Okay. I'm even going to copy and paste that so you have a better idea. What are we talking about? Okay. Snipping tool. That's the snipping tool. I will. Now you're going to start having some illustrations there. The notes. Okay. See the illustration. Someone left a message here. Let's see, chat. Okay, good. Good. Thank you, Vanessa. Thank you, Ashley. That's the situation. Okay. And it applies for charges that are positive as well. You can put a positive charge here, but the only difference is that if you release the other charge from rest, it's going to move away from the positive charge, right? So just use conservation of energy, just before here. Oh, let's put one more. Now let's put something else here. Not just initial electric potential, but we also have initial kinetic energy. Okay. And then we are going to need also the final kinetic energy. Can you relate to that now? It's very important to make those analogies, right? Because you're already very familiar with this type of problem. When we start to see a new problem, it looks like it's going to be much different, but it's not going to be that much different whatsoever. It's going to be in a way, very similar. Okay, and that's the analogy that we have. Let's continue going here. Okay, next step. Okay, this zero disappear. This guy here becomes negative. We have an equal sign right here. I can put the Q in evidence. When I put the Q in evidence, this Q disappear, right? And then we are left with this equation right in here. 2 goes to the other side, M go also to the other side, and we end up with this solution with a square root right in here. So that's one good example of how you solve problems using electric potential. Okay? And now we can start talking about electric equipotentials. Let's see if I get a better illustration. This one here. Interesting. Oh, yes, must be here. Let's see. Let's see if I can get a good. No, not this one. Maybe this one here. No, not this one either. Let's try this one here. Nope. Yeah, unfortunately, it doesn't look like I have, but I'll have to do that from scratch, okay? I'll have to do that from scratch. I will show you, since I did the electric field of a point charge, I will be able to superimpose the figures that I have right here for the electric field, okay? So here you go. You went through this exercise of determining the electric field. Okay, now we have okay, we're going to use this one right in here. That's a very good one. And I'm going to keep on shifting back and forth with the other one. Okay. Now, oh, here you go. I have the equipotential here. Oh, but let's start from scratch anyway. Okay. So go back to the equation here for the electric potential of point charge, right? Let's take a look. The electric potential of a point charge that you must memorize. Okay, here you go. That's the potential of a point charge. Okay. The E here stands for electric, right? The G here stands for gravitational. That's for the point. Notice that this electric potential is a function only of the distance on the charge. It's not a function of the angle, right? It's just a function of the distance. So what does it mean? It means that at this point right here, the electric potential at this point must be the same as the electric potential at this point, which must be the same as the electric potential at this point, which is the same as the electric potential at this point, and so on, okay? Because this electric potential have what we call spherical symmetry, okay? We can come up with a equipotential surface that's going to be a sphere as well. That's what we have here. Okay, so this is one equipotential surface. The equipotential surface of a point charge is going to be a sphere. Further down, we are going to have another equipotential surface of a different value. Okay, and so on. Strictly speaking, let's go back to my notes. Go back to my notes here. I'm going to copy that. Strictly speaking, we are going to have, for instance, I'm going to call it V1. That's going to be my first equipotential surface. Strictly speaking, the electric potential at that surface is going to be something like that. That would be the electric potential for a point charge, a positive point charge. I'm going to put it lowercase q, so we are, we are consistent with what has been drawn there. Next one is going to be R2. And then I'll change it to V2. Do you get the idea? And V3. Things become more and more complex when we have different charge distributions, right? There you go. That's one equipotential. That's another equipotential, right? And that's another equipotential right in here. 3 different equipotentials. Okay, and the equipotentials has this characteristic, important characteristic, that the electric field, let's see if I can copy that and superimpose. Here you go. I couldn't. Okay, the electric fields, they are perpendicular to those equipotentials. You know what? Let's see. Let me just copy something else here. Just the copy everything. Okay, here you go. We don't need that. We don't need that. We don't need that. Let's say I don't need that. I don't need the y-axis. I don't need the. I have everything that I need. Now I'm going to copy that and superimpose to my equipotentials. And I'm going to centralize this thing now. Let's see if I can do that. So the equipotentials has this very interesting characteristic that the electric field is normal to the equipotential. You get the idea? Okay. This angle here of the electric field with respect to the tangent plane to the equipotential is going to be 90 degrees. Okay. And that's the important thing that we are using in this experiment. in the experiment that we are performing. Q greater than 0, let's put it here. I want to do better, right? I gotta put my vector starting. Forget it. Let's do it. Otherwise, it's gonna become too much. All right. There it is. It's not centralized, huh? It's not centralized. Let's see if I can get a better centralization here. It's either not centralized or these surfaces are not exactly vector, 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 vector. Let's see if I can get it a little bit more like that, right? Okay, so that's what we have for my equipotentials. Here's my charge, right here. The middle is the charge, and that's what you have to know. Another important piece of information. Okay. And now equipotentials. This idea of equipotential is using the experiment that we are doing, okay? Equipotential surfaces are exactly what the name describes, okay? Around a charge distribution, comma, we have equipotential, we have potential surfaces that we have with the same potential values. Okay? For the case of a point charge, these equipotential surfaces are spherical. And they do, very important too, they do not intersect with one another. Okay? They do not intersect with one another. That's the simplest one that you can visualize. The next simpler equipotential surface is that for a uniform electric field. Okay. So let's take a look. The first at the electric field, at a uniform electric field. Okay, we don't have it here, but we are going to see further down here. Must be the other one. Okay, it is here. Remember that the electric field of a large plate generates a uniform electric field, like this one. I want one without the charge there. Okay, I will copy this one. Okay. And I will paste that here. Okay, and then I'm going to take out this charge that I do not need. All I want is the electric field there. And let me see if I have it right. Yeah, I have it right. Here I have positive charges. Sigma that you have here means surface charge, surface density of charges, surface density of charges. The field outside is 0, and the field inside is non-zero. Okay, and that's the type of configuration that we are doing today. Okay, and then what else do you have? Okay, we have the following. Let's go back to our notes, right? In our notes, I mentioned to you that the electric potential of a point charge is something like that, right? That's what I mentioned. But for a point charge, but for a uniform field, there is also a relationship between the electric potential and the electric field. And it's going to be a linear relationship. It's going to be minus EX. Okay? It's possible to derive that. And consider this one is going to be the position 0 of your X, right? Going from the left to the right, the potential increases from the left to the right. The increase in electrical potential is contrary to the direction of the electric field. Okay? And the electric potential is increasing linearly. If we have an electric field just like that, it means that my electric potential surfaces are going to be, planar surfaces as well. One planar surface here at a given electric potential, another planar surface here at another electric potential. I'm not considering, okay, and another electric potential surface right here. Strictly speaking, the field is not exactly like that. We just should have a little bit of a deviation, okay, from the horizontal direction. And here the field would have a slight deviation also from the horizontal direction. That's what we call the borders effect. And that's something we can see in the data that you have there. And again, the equipotential is going to be, the electric field lines are going to be perpendicular to this, normal to this equipotential. And I'm going to put another, here you go. This one is going to be, I'll call that equipotential V1. Okay, equipotential V1. Equipotential V2. Okay. That's gonna be 2, which because it's more negative than the other one, it means that's going to be less, right? You know what? I'm gonna put a magnitude so we can make things easier. Magnitude of that. If we put the magnitude, then this guy here becomes greater, okay? V2 V1. And then we got this other one, V3. V3, okay, it's like that. Magnitude. V1, V2, V3. That's what I want. And, you know, and then we have others too, right? It's not just the parallel plate that we have. We also have the other types of charge distribution, but let me update my notes, right? Okay, so here we go. Equipotentials. The idea equipotentials is used in the experiment we are doing. Equipotential surfaces are exactly what the name described. Around a charge distribution, you have potential surfaces with the same potential values. Okay. For the case of a point charge, these equipotential surfaces are spherical and do not intersect with each other. We have, let's say, we have surfaces with the same potential values, and let's say, I'm going to put it here, and they do not intersect with one another. Okay. No matter what type of equipotential surface we have, the equipotential surface, they do not intersect with one another. Okay, for the case of a point charge, these equipotential surfaces are spherical. Okay, the next simple equipotential surface is that of a uniform electric field, which has planar equipotential surfaces. Okay, that we saw. Next would be that of a charged rod, infinitely long charged rod distribution. Do you remember that? We did that as well, right? Which we determined the electric field of a charged rod using Gauss's law. Let me see if that's the one here. No, it's not this one. It's another one there. And that charged rod distribution, here you go, Gauss's law. Okay, right in here, right? We have this, cylindrical distribution, right? If by the same token, and I'm going to reuse that as well in the following way. Okay, here you go. Here's the electric field, right? And here's the area vector. And I'm going to use this one as well. Electric field, electric potential energy. Here you go. Next. Okay, charged rod. I'm going to put it here. Infinitely long charged rod. Infinitely long charged rods. And now I'm going to do the following. Oh, right here. In the case of the charged rod, let's put I'm going to change the color, right? Here you go. Here, those are no longer the area vectors. Now I'm going to call this one the electric field vectors. For this reason, I'm going to change their color. Outline red. Okay, here you go. And this one, you don't need that anymore. Here are my electric fields. We have one electric field line here. We are going to have another electric field line here. It's going to be a little bit weaker, right? here as well. It has those electric field lines, they have cylindrical symmetry. Another electric field line here. Another electric field line here. And I repeat the same for this lower surface. Even better, I'm gonna copy this one and invert the vector size and position. Position, no, that's not what I want. It's not size, should be size and format shape. That's the one. Invert the arrow. Okay, here you go. Invert the arrow. Invert the arrow. Invert the arrow. It's not a uniform field, right? And now I don't need to label those surfaces. I don't even need this one here. Oh, not this one. This one stays. Let's see. Yeah, it has to stay. Okay. And what should go? The one should go. The number 2 should go. Okay. And then what we have here? Here is going to be one equipotential. Here is going to be another equipotential, and so on. Okay. And I want to take this one out. It's better. So you have a better drawing. Oops. You go draw it. Yeah. I will give a little color to this guy. Yeah, I don't need that. I don't need that. I don't need that. Here you go. Here's the rod. Here's the rod, right? Here's the rod. And now we have this equipotential here, for instance. At the distance R1. Again, I'm going to put it dashed so you know. Yeah. Can do better than that, right? Let's do a better dash here. I want to see this one here. What do you think about this one? This one? No. I prefer the other one. Still not what I want, but let me see if this one goes better. No, I like more this one. Yeah, let's leave this one. Equipotential surface. Another equipotential surface right in here. It is perpendicular to the electric field. Another equipotential surface right in here, and so on. Right? And we're going to have V1 here. V1. Subscript. I will change color. And because we have symmetry, this one is going to be V1 as well. The equipotential in this case is a cylindrical surface. That I'll call R1, right? Radius 1 from this cylinder. Let's call that R1. Radius 1 from the center of the rod, okay? And then we're going to have an R2 for this other surface from the center of the rod as well. And next one here is going to be V2. V2, yeah. Okay. So try to picture a cylindrical surface. And I'm gonna emphasize that this is a cylindrical surface. How I'm going to emphasize that? Let me get that here. By drawing this little cap here, this one here. Okay? I'm going to emphasize that this surface is a cylindrical surface by adding those two caps there. Okay, better now? And now I can move a little bit further away here, right? A little bit further away here. And we can do the same for this one, for this other surface too. You can put another cap there, okay? If we have a spherical distribution of charges, you're also going to have a spherical equipotential surfaces. And then you can have more complicated ones, okay? More complete, but those are the simplest one to visualize on charged rod distribution. In this case, the electric fields, right? Electric fields point away or towards, depending if it's a positive, the rod, right? The rod, and the equipotentials are cylindrical surfaces. Okay? And then, no, next, the spherical shell is the spherical shell. Okay? In the case of the spherical shell, the field is zero inside spherical shell. Let's put of radius r. Okay? In the case of the spherical shell of radius r, I want to put radius r elsewhere. In the case of spherical shell, of a spherical shell for the spherical shell, the field is zero inside the shell and decreases with the square of the distance outside the shell. The equipotentials in this case are spherical outside, but inside, because the field is zero, the potential will have a constant value that coincides with the equipotential at the surface of the sphere, of the shell, of the spherical shell. Okay. Can you picture that? Those are what we say in words, right? But in terms of pictures, let's go here. I have my shell. Here you go. That's my shell. Let's see. My shell is somewhere. Someone else trying to come in. Let's see. Cell 943. Let's see if I have a spherical shell right in here. Okay. Spherical shell right in here. See that the electric field is zero? The electric field. Don't forget, what you see here is a Gaussian surface, okay? But the Gaussian surface coincides with equipotential. Okay, so here it would be one equipotential, further away would be another equipotential, another spherical equipotential, so on. Here inside, we have this funny behavior. It's not going to be an equipotential surface, but it's going to be equipotential volume. Okay, because the electric field zero is going to be zero here inside, the electric potential is going to be a constant throughout this whole volume. Okay, and which is going to have a value, potential value that coincides with the value on the on the surface of the shell. Okay, I can write that down in my notes. Next is the spherical shell of radius r. In this case, the field of the shell behaves in the following way. One, E is 0 for little r less than big R, and E decays with the inverse of the square of the distance for r greater than r. Okay. In this case, the field of the shell behaves in the following way. In this case, we have the following. Okay. We have the following. Okay, here you go. One, the field of the shell is okay. Okay. Is equal to 0 for r, and E indicates the inverse of square distance for r greater than r. We'll go even further than that, okay? And C for r equal to big R, E is going to be given by KQ, okay? Let's put it this way, divided by big R, okay? Because remember, it's a spherical shell. The spherical shell behaves just like a point charge, right? Outside the shell, the behavior is just like that of a point charge. Suppose that the field, let's say next the spherical shell of radius r, and charge and net charge q. In this case, we have the following. The field of the shell is 0 inside the shell. Oh, by the way, it's r squared. It's not r, it's r squared because it's the field. You go cancel like that. And then we have something else. What about the potential of the shell is? Okay. V decays with the inverse of the distance, okay? Because now is the potential. V is constant for r less than big R, and exactly at the surface, the potential, oh, what did I do? I want to take out the square, here you go. Exactly at the surface, the potential is KQ over R. It's not difficult to memorize that, right? It's a different charge distribution, but it's very similar to what you saw before. Okay, V is constant of the distance, and by the case with the inverse of the distance, I mean, I'm going to spell that out. Like that. And point charge, right? Okay. These are examples of simple equipotential surfaces. Equipotential surfaces. These surfaces become much more complicated whenever we have different, whenever we have more involved charge distributions. Okay. And let's see if we can get give you an example in the internet, right? Equipotential surfaces of a dipole. Okay, a dipole is very complicated. Okay, here you go. Here's the dipole. See, it starts like a spherical surface nearby this charge, but as the distance increases, the spherical equipotential start to diverge, right? The equipotential start to diverge from spherical potential, because now this negative charge is going to have the effect of this negative charge at this point is not going to be negligible anymore. Okay, but you can see, right? Here you go. The spherical is not exactly spherical, right? But it's a surface. It's kind of spherical, a little bit off center, Okay, and this, for those types of surface, we don't even have a name for them. Okay. Potential for surface or electric dipoles and other equipotential surfaces here. Okay, here you go. Constant electric field. Okay. There are examples of these are examples of simple equipotential surface. The surface become much more complicated whenever we have more involved charge distribution. See, for instance, the equipotentials of an electric dipole. Of the electric dipole below, right? I'm going to copy and paste from there. I'll copy that. Copy that image. Good. Didn't paste it. Doesn't look like it did. Let's try copy. Let's see. Yeah. Okay, good. Electric fields and equipotential surface. And don't forget, these electric fields are going to be perpendicular to the equipotential surface. In all these cases, he pasted before, I didn't notice it. In all these cases, the electric field is always normal with the equipotential surface. Right? Always. Okay. So that's what we have, 9:52 right now. I want to take attendance. Any questions? Did I miss anything from you? Did I miss any questions from you? Okay. So those are the notes. Okay, and let me just summarize what we have covered so far, right? It's lots of stuff, and because there's so much material, most likely you won't be able to understand everything at once. Maybe you might understand one thing or another one, right? So here you go. This is the map, right? Map of the course. I like to call it the map of the course. Okay, here. Electric charge that you must understand. Everything else from the course. Everything else until the end of the course depends on this basic concept that you see there, electric charge. And then we have this idea of the quantization of charge, which was obtained through the Millikan's oil drop experiment. And by the way, when Millikan was doing this experiment, he interfaced himself with Thomas Edison at the time, and Thomas Edison was convinced the electric charge was quantized. Yeah. And then we have the electric force, we have the electric field, and next in line is the electric potential. Okay. Oh, even better, electric potential energy, right? Energy comes before the potential. And then you have the electric potential. And within the idea of the electric potential, we have the equipotential surfaces. Equipotential surfaces, okay? If fields are normal, to the surface, to these surfaces. That's the map of the course so far, what we have covered in the course so far. Okay. And I'm gonna get my spreadsheet here. P07. Let's see if I get it. Must be this one. Let's see. Yeah, I got it. Lab. Okay. Lecture attendance. Okay. Today is the 21st. Strange. Huh. Right. Jacqueline Arieta Hernandez. Are you there, Jacqueline? Just send me a text message, a chat message, or you can say I'm here. I see Jacqueline is here, but looks like she's away from her computer. Next, Sky. Are you there, Sky?
I'm here.
Thank you. Vanessa Escalera. Hello, Vanessa. Okay, I cannot hear from you, Vanessa, so I'm gonna put this out.
I put it in the chat that we're here.
Wait a minute, I didn't hear. What did you say?
Put it in the chat that we're here.
Okay, good. Jacqueline put in the chat. Okay. For some reason, you didn't accuse you send a message. Okay, but I see it now. Thank you. Jacqueline, okay, and let's see, the Vanessa Scalera is also here, right? Okay, good. Okay, Ashley, are you there? Thank you, Ashley. Next is Corina. Thank you, Corina. Norberto Lopez. Thank you, Norberto. Next is on another Vanessa, right? Vanessa Mena.
Here.
Thank you. Yorgo, are you there, Yorgo?
Yes, I'm here.
Thank you. Lizelle. Vince Cruz. Hello, Lizelle, are you there? Okay, I'm gonna put a star in Lizelle's name. Okay, let's see. Okay, next is Paul Zapata.
Here, Professor.
Thank you. And next, here you go. We have a total of 9, 10 students. Okay, good. So let's have our break right now. Okay, break from 10 a.m. Let's round it up. 10 a.m. to 10:15 a.m. And then we can continue with our lab. Okay. So I see you in 15 minutes. Okay, I'm back here and I'm going to share my screen and we are going to have I'm going to show you a video that I saw. It's very similar to what this video that I'm going to show is very similar to what we used to do there at LA Harbor. Okay, it's on YouTube, electric field lines. Let's 20 minutes long, a little bit long, but let's see. Let's go ahead anyway. And then we can start with our experiment, right? With our data. Let's play it.
Okay, so here's the experiment. We're going to,
Here you go. Here's the paper that I mentioned to you, okay? The conductive paper. And here is one of the electrodes that I mentioned to you before, that electrode that's created with a paint, a special type of paint, a special type of ink that has little flakes of metals dissolved in it, okay? This device that you see here is my so-called battery, okay? It's not exactly a battery, but it behaves like a battery. It's what we call a power supply. We can adjust the voltage of this device. And here is his multimeter, the guy that measures electric potential, okay? And let's play a little bit more and
it's called a field mapping experiment. We're actually going to map out electric field.
it's not that we're going to map the electric field. No, he didn't say it properly. We're going to map the electric potential. And from the electric potential, we are going to deduce the electric field distribution. Okay? That's what he's mapping. He's mapping the electric potential. And from the electric potential, he finds out what the electric field. There is a relationship between the electric field and the electric potential. Okay?
And we have to do a little bit of theory after this to show you what's going on here. And again, you're not going to get this until you get to chapter 24, I think it is, in Survey, which is 3 weeks away, 2 weeks away. So anyway, but you do need to know something about that in anticipation of that theory to figure out how to measure the strength of an electric field. Okay, so we have here
Do you see the two electrodes? And that's how the paper looks like. There is some little crosshairs here, okay, because they are separated by 1 centimeter. You saw that, and he painted the electrodes on the paper.
rather strange looking black piece of paper. Actually, it's a kind of thick black.
What this distribution here represents the distribution of a parallel plate, very large parallel plate. Even though it's in a two-dimensional paper, this guy, it behaves just like a parallel plate that's sticking out from the paper, okay, from the black paper.
Black piece of paper, and it's graphite coated or graphite impregnated paper. Graphite is carbon. Carbon is in the middle of the periodic table that has 4 electrons and is happy with them, and it's also happy to share. So that's the basis of organic chemistry. In any case, I've drawn on this. So carbon is a semiconductor. It conducts a little bit of electricity, but not very much. It's not a very good conductor, not like steel or copper or whatever, any metal, almost any metal.
Do you see here? That's the cork boards that I mentioned to you before. Okay, we have those cork boards as well. Here are the pins, 2 of the pins only. The cork board is a very good dielectric material, and then that's where we put this paper over this cork board surface. And by the way, I'm putting a link for this video, okay? In the notes. In the notes we have the link for this video.
But it's a semiconductor, and I need that because this voltmeter, which you've already used it before, has to.
See, he mentioned that he referred to this device as a voltmeter. Yes, that's another name for it. Okay, we call it, but in reality, we call it multimeter because it is a voltmeter, it is an amperimeter, voltmeters to measure voltage, amperimeter to measure current. Okay, sometimes it measures capacitance as well, which is another quantity, and other stuff as well, and even frequency of a circuit. That's why we usually call it a multimeter, okay?
To have something to go through it to measure. In other words, it's got to have some current to go through the wires to be able to measure what that current is, or it's got to have something going on. If it's measuring voltage, it's got to have something going through the electrical system in the meter to cause it to be voltage. Let's not get too much into electronics. So on this piece of semiconductor paper are drawn two parallel lines with honest to goodness silver ink. Every one of these patterns, like, it's got 50 cents worth of silver on it. But don't go scratching them off and try to sell it. Anyway, or maybe it's only 15, but it's got some silver in it. So silver is a really good conductor, like it's one of the better metal conductors, and so it conducts electricity. And it can conduct electricity from one side to the other, or from the middle to the outside, and it can set up an electric potential. We'll get to that later. Electric potential here and another electric potential here. So we have two leads on meters. One's a black lead, one's a red lead, and there's the red lead over here. It's connected to this black lead over here at the power supply, and so we can measure voltages. In fact, I got this set at roughly 6 volts. So let's check that out. Okay, it's a little bit high. This is very delicate.
Okay, so what he's measuring here, what he's doing here, he's measuring the output of this power supply. Okay, that's why he says 6 volts. It looks like he's adjusting the power supply to 10 volts. Let's see what he's gonna do.
So that it stays at 6.
6 volts.
So I can turn this down just a little bit more. So closer to 6.
Yeah, okay. He wants to set it to 6 volts. We usually set it to 10 volts. This power supply.
Oh, that's close enough.
Yeah, 599.
That's 6 volts. So I'm going to connect this red. First of all, I'm going to thin this down so it's not so curled up.
See how we perform the experiments. First, we put the pins
These are
at the
metal pins,
edges.
which means they're conductors, and they will transmit the voltage.
Okay, we're just fixing the paper into place. That's all. Those pins has no other pins here at the edges has no other function but to fix the paper in the cork board. Okay, they are not going to be part. Those 4 pins are not going to be part of the circuit whatsoever. What's going to be part of the circuit are the pins that are going to go here in those 2 electrodes. Okay,
voltage to wherever we put this on. So I've got these pins. I got these little clips here on these pins, so that
okay.
Like
see. Oh, let's take a look. Okay, see, it's the same pin that we have. Okay, the same of those 4 pins. But then what we have here, we have an alligator connector. You know, it's just like an alligator, the mouth of a little alligator, and he clamps on the pin. That's how we do as well in the lab there at LA Harbor.
Itself, and the reason for that is. You'll learn later, as I mentioned earlier, that the electric fields can be set up by single charges, like we talked about with Coulomb's law, or they can be set up by a whole bunch of charges. There's a whole bunch of charges in this wire, and they're put there by this voltage supply, which pushes the charges in the wire.
Remember, red is positive, black is negative, right? Positive charges, negative charges. So you have an electric potential difference. When we have an electrical potential difference here, it means that we have electric potential energy there. Since this device has electric potential energy, if we are smart enough, we can figure out a way to do some useful work with this power supply. Okay?
I'm going to connect.
So here you go.
Very carefully. This wire to with this push pin, and I push it.
The pin is connected exactly at the electrode. Okay, that's going to be the positive charge. This electrode becomes positively charged. The moment that we connect it, it becomes positively charged.
It's fairly hard, so that makes a good contact, good electrical contact with that silver line. Okay. You know, from the song, there's a silver lining in anything. Well, this is a silver line. It's not silver line.
And now he's going to do the same with this other one that's going to become negatively charged, right?
So this black lead here is going to be connected to the other line, and I'm going to push it down so that it's nice and flat. There is an electric field set up by these wires.
Okay, Now we have negative charges here in this electrode, and we have positive charges in this other electrode. At this very moment, we have this electric field that going from the positive to the negative, and the electric field should be very close to that of a uniform field. Uniform field means linear increase of the electric potential, okay?
And I really don't want to have it mess with the electric field set up on this pattern. It's just kind of like a two-dimensional electric field. So I'm getting those wires away from the pattern. That's why I've got them put up that way, and so they're not resting on the patterns. So I don't want the electric field of that wire to be fighting the electric field on this pad. Okay, so we've got them all hooked up. And if I look over here at this, take a look at the meter, look over here on this,
Okay,
it's
so
almost 6 volts.
do you see what he's doing? And that's his hands in the way you cannot see it, okay? You cannot see, but what he's doing, he's getting the positive of your meter and he's touching that positive electrode, but his hands in the way you cannot see it. That's why it's showing 6 volts here.
Here, it's
Okay.
6 volts here.
Yeah, okay, now you can see it. Okay, see that? The probe, and let me see, where is this negative? Oh, this negative here. Okay, he was not careful about that, okay? But this negative of the multimeter is also going to the negative of the power supply, okay? That's your reference, the reference to make measurements. We can put it either here in the negative of the power supply, or you can put here in this other pin as well. We can do it either way. I'll do that. We do that either way, okay?
Well, here, it's 5.93, 5.93. It's 5.93 all the way from the left to the right end of that pattern, of that line, that silver line. And again, I guess the meters change a little bit, so it was closer to 6, but it's 5.93. And over on this side, the voltage is 0.
It should be just 0.
It's not quite 0.
Very small
It's
difference,
close
very
enough to
small,
0.
it's negligible, this difference that you saw.
So on this end, it's a little bit not quite good. Okay, look. That's pretty much 0 everywhere. Okay, so this is called the 0 volt.
Okay, so now you have to visualize the equipotential surfaces, okay? Here is 0, here is 6 volts. So between 0 and 6 volts, the electric potential is going to increase. So let's say at the very first centimeter here is going to be 1 volt. At the next centimeter is going to be 2 volts that you're going to measure. 3 volts, 4 volts, 5 volts. Okay, it goes linearly just like that because the voltage goes linearly with because the electric field is uniform. Okay.
Line, and this is the 6 volt line. And we call them equal potential lines because they have the same potential, the same voltage. Those are not quite interchangeable. The same voltage is 0 on this line and 6 on that line. We're just not, this is a semi-quantitative experiment, so you can't get too fussy about, oh, is it 6.03 or is it 5.8, 5.92 or what? It's 6.
By the way, this experiment, he said semi-quantitative experiment. I disagree with him. If it's done properly, if you know what you're doing, you can get pretty good results with those experiments. Okay, I have been able to plot graphs with my students and determine the strengths of the electric field. Okay, and that's what you're going to see too whenever we plot all the graphs that we have to plot. Okay.
Oh, irritate a little bit, but not much. Okay. So we're going to be drawing some lines here and measuring some values, and you know, they're kind of crude. So you can't really do a sophisticated error analysis here because it's a semi-quantitative experiment. That's okay for one.
And again, I don't agree with him. It's not a semi-quantitative. It's a very good experiment.
We're in the universe, an electric field that's emanating from these 2 lines. Now, my job, your job, is to measure the locations in the electric field. We've already done the 6 volt line and the 0 volt equal potential line. Your job is to find the 1, 2, 3, 4, and 5 volt potential line, equal potential lines, and mark them with a piece of chalk. And I'm not going to do that because I don't want to mess up this pattern. But why do we use chalk? Because chalk is not a conductor. It's not even semiconductor. Lead pencil, lead is not lead. It's graphite. Look, graphite. That's what this thing is made out of, and it's a semiconductor. So you don't want to use. You don't want to draw on this with a pencil because it's like adding more lines, more equal potential lines or whatever to the pattern. You don't want to do that. So we're gonna use pieces of chalk and we're gonna mark on this grid, which is by the way, centimeter by centimeter grid. We're gonna mark on this grid where all the lines, where all the points are that are, not all of them, but many of them, that are 1 volt, 2 volts, 3 volts, 4 volts, and 5 volts. Okay, so let me take this and look over here. That's 0 volts. We checked that before. This is about 6 volts. We checked that before. So somewhere in the middle ought to be about 3 volts. Oh, and
Yeah.
let me move that. Okay, there it is.
3 volts will be exactly in the middle between the two plates, okay? Yeah, he's close enough. Would be like 3 centimeters from the negative plate.
Surprisingly, not surprisingly, exactly in the middle, because 3 is exactly the middle between 0 and 6. Okay, so there's 3 volts. So I'm going to find another 3 volt point here, and I'll put it back there. I'm going to find 3 volt point here, put it back here. Then you'll find probably, depending on the quality of the pattern.
Okay, so once you find a place, let's say with 3 volts, you go ahead and say the X position of that place of 3 volts is going to be, whatever. The Y position is going to be whatever. Just like I explained in my PowerPoints last time, right?
That line basically goes to us straight across, or pretty much straight across. So put a bunch of dots here, 12, 15, 20, whatever dots, just what we just did, and put a dot where the probe is touching the paper, and then connect those dots. Again, that's called the equipotential line, and that's the 3 volt equipotential line. Okay, let's take a look at the 2 volt line, for instance. So the 2 volt line ought to be closer to the 0 volt equipotential line. It's going to be over here someplace, and there it is. It's pretty much, I kind of planned it this way. That is, these two lines are 6 centimeters apart, and we've got 6 volts here, and so it's about 1 volt per centimeter, right? With every centimeter, here's the 1 volt line, it's at 1 centimeter. There's a 2 volt line, it's at 2 centimeters. There's a 3 volt line where it's showing up at 3 centimeters. There's a 4 volt line, it's at 4 centimeters. There's a 5 volt line, it's at 5 centimeters. No surprise, right? So what you're going to get here, and I'm not going to tell you what you're going to get elsewhere, but what you're going to get here in between these 2 lines are 5 parallel lines, essentially 1 centimeter apart. And we want to talk about that a little bit later in terms of how you analyze these. So, but then when it comes out here, let's look for the 2 volt line here. So 2 volt line, and just keep poking around until I find the 2 volt line and getting warmer and getting warmer, almost there. Okay, there's a 2 volt point. And it's going away from this second line here, it's going off this way. So you want to look for that 2 volt line everywhere. There's got to be a 2 volt line out here someplace. Okay. There it is. The 2 volt line is way
Okay,
out
2
there.
volts.
So
But now he's measuring outside this volume, okay? Now he's measuring out. When you go outside the volume, you can see that, the 2 volt line is expected to be here in this region whenever it is between the 2 plates. As you move away from the 2 plates, this point is going to bend a little bit, okay? That's what we call the edge effect, okay? The field is uniform only in this volume here that's bound by those 2 electrodes. Outside these electrodes, the field is start to deviate from that of a uniform field. That's why you're getting this 2 volt measurement in this region instead of this line right here, okay?
This white border from one side all the way across to the other side. There's a 2 volt line.
Same thing on the other side.
So put little dots there and draw that. Don't draw the line on, because if you start smudging this, if you start drawing lines with the chalk marks and the chalk line, you're going to get it all smudged up. So we're going to produce this pattern and take it out, take the weeds away, and then with a piece of chalk, draw a line from one side to the other that mark the 2 volt potential, equal potential line, and 3 volt, 4 volt, 5 volt, and 1 volt. So you get a pattern. We have to talk about what you do with that pattern.
And we're going to get this pattern.
Okay, and then we'll do one with 2 circles. And I want you to especially measure the voltage inside of those 2 circles, and make a note of that and think about what that means. You may not understand really well what that means until we get to the chapter on electric field and electric potentials and things like that. But see what you get experimentally, and if you don't know quite what to make of it, at least report what you get experimentally. So that what's the voltage inside of each of those circles? And look them up like this. one wire, one circle, one wire, the other circle. Okay, so I'm not going to fill out this pattern, but you can see that the lines kind of diverge as they go out here and they go out here, and you want to look for lines everywhere. So here's a 1 volt line here. There's a 1 volt line out here someplace like here, and there's no 1 volt lines in here until I get over here. And there's another 1 volt line. Okay, so that 1 volt line kind of wraps around a little bit. Okay, so that's the way you do this experiment, and finish up all 5 lines. If they start to get kind of confusing, maybe you want to draw a little bit of the lines to make sure you know that's the 1 volt line, that's a 2 volt line. Especially for the circles, it's going to be a little bit more tricky. And then we will take a photocopy of this so that you can work on this, do an analysis without smudging up all your lines. And so at that point, when you're done with both copies, or if there's time in between, if you're done with one copy, we will run out and make photocopies for you so that you can work on them without smudging. Okay, that's it. It's pretty simple.
Okay. So that's the experiment that we do. I think you did a pretty good job. The other 15 minutes is just the theory that I have covered. So we're going to stop right here. And here you go. That's the link. I'm putting, like I said, I'm putting the link. That's the link right
Ever
here.
wonder why so many people say they?
It is in my notes, this link. Let's see, this one here. Okay, let me erase that stuff. Issue the experiment. Okay, and now we are going to start working on the spreadsheet. But before I do that, let me post something else. I need to post those 2 documents there in your folder. Okay, we're going to be using those 2 documents. And even better, let's see if I can post in Canvas. See here. I want to go to Drive. Google Drive, okay. (2024), that is how I'm gonna do that. I'm gonna put that in Canvas for now. Yeah. This one. Lecture. Okay, new videos, Wiley plus flyer, syllabus. And let me see how many students. Okay, let me get my documents, the documents that really matter. The documents that I'm talking about. Let's see. Lab reports. Some lab reports must be here. This one. Yeah, I need that. Let's see. Let's see. I'm gonna create a new modules lab. Add modules. Okay, and I'm gonna change it to P07. P07 significant figures. You go. You're going to need that, and I'll let you know exactly what it's all about. Okay, and we're going to need another one too that we used last semester. Confidence level, let's see. That here. No, let's see how I want to get that one. 2023. Let's go to the fall. Might be here. Confidence, level. Oh, here you go. That's the one. Those are the 2 documents that we're gonna use throughout the whole semester. And I have to publish, right? Let's increase the ident. Good. Go ahead, download those two documents. And I'll at the right time, I'll tell you how you're going to use those two documents, okay? Please download both of them. When the time comes, I will tell you how to use them, okay? So here you go. So we're using the multimeter to measure voltage. We are using the ruler to measure the positions of your point. He didn't do that, okay? He just said, you know, there was a given position there, but we're using the ruler to measure the positions of your point. And don't forget, the resolution of the ruler is 1 millimeter. That's how, you know, that's how we are going to use those are the significant figures that we are going to use. We're going to use, you know, you might have seen it different from other professors, but I like to be very conservative on those experiments, okay? Use the 3 decimal places of the resolution of the ruler as your as the limit of your significant figures, okay? Significant figures. That's how we're going to do that. So if you measure, for instance, exactly, so if you, I'm going to example, right? So if you measure exactly 2 centimeters, right, with the ruler, you should report 2.0 centimeters, but then you have to convert that in meters, which is going to be 0.020 meters, okay? Those are the significant digits of your measurement. And I am going to boldface them to emphasize that, okay? Make sense? Okay, so that's the conservative way that I like to teach my students. We do not go for more significant digits than that when we are using the ruler. And at this point in time, let me get my spreadsheet. My spreadsheet here and see here. Blah, 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 blah. Yep. Let's sort by column B, no, column C. Okay, so we have group number one. Lizelle, are you there?
Yes.
Okay, good. So good. So we have here 10 students. So we have 4 students in group 1, 3 students in group 2, and 3 students in group 3, right? And let's get that here 4. Make sure open your spreadsheet, okay? make sure you have everybody. Do you have your spreadsheet there? Jacqueline, do you have-
Professor, can you hear my mic? Is it working?
Yeah, it's working loud and clear. Loud and clear. Okay, so Jacqueline, did you do you have your spreadsheet there open in your computer? I want you to open the spreadsheet right now. I'll do that the same. I'll do the same here. Let's see here. Oh, no, it's not full. LHC 2024, P07. Let's see, lab, illustration, lab. Good. Raw data. So I'm going to lab number 1. Here you go. I don't want to. Here is the spreadsheet that you have right now. Okay. Everybody should have the spreadsheet there in front of you, and I'm gonna go through everyone. Jacqueline, do you have your spreadsheet there open? Yes, okay, good. Next is Yorgo. Did you open your spreadsheet there, your group spreadsheet? Yorgo? I can't hear you, Yorgo. You might want to type there in the chat box. Okay, I'm gonna put a little star here. Lizelle, did you manage to open your spreadsheet?
Yeah.
Okay, good. So Paul Zapata, did you open your spreadsheet?
Yes, I did.
Good, great. Vanessa? Do you have your spreadsheet? Good. Norberto Lopez? Did you open your spreadsheet?
Yeah, I was able to.
Okay, good, thank you. Vanessa?
Yeah, I was able to open mine.
Okay, good. Vanessa Mena, right? I meant Vanessa Mena. Next, let's see. Vanessa Escalera, okay, Sky. You open a spreadsheet?
Yes, I opened it.
Good, thank you. Ashley? Ashley, yes? Okay, good. Ashley and Corina, right? Okay, good. So everybody has the spreadsheet there in front of them. That's good. We can proceed. And what we are going to do? Okay, let me first explain what we have here. Here are the measurements in volts, okay? If you go through those numbers here, in my case, I have 1 volt, but not exactly 1 volt, but it's close enough, okay? You cannot always measure 1 volt. Sometimes it's very difficult to get exactly 1 volt, right? So you get a measurement that's close enough. Like this group got 1.022. See at the top here? It's okay to have 1.022. It's not exactly 1, but 1.022 is only 2% off the actual value that you want, okay? So those are all voltage values. But in addition to the voltage values, what else do you have? You have the coordinates of this point, X and Y position. See that? X here is 0.016, right? And 0.016, 0.0145, let's see, 1, 2, 3, yeah, okay, 0.0147 and so on, okay? It's all in meters. Notice that the units here in volts, oh, volt, meter, and meter, right? And then we have the Y coordinates as well, okay? Y coordinates are 0, 0.00, whatever, and so on, okay? What I want you to do, there's a little trick for plotting those equipotentials, okay? You're not gonna find this trick anywhere else, okay? If you're my students, you're gonna find out how to plot those equipotentials. So when we do an actual experiment, you will be able to plot the actual equipotential with this data that you collect, right? And the way you do it is like that. You highlight those numbers, X and Y coordinates, okay? At this point in time, you should already know how to plot a graph with Excel, right? But and that's what we're doing here. Highlight all the X and Y values. Okay, and then insert, go to chart, always get the scatter chart, and use the ones without lines, okay? Just with the data points. Here you go. That's my equipotential for 1 volt. That's all. Those are the points of my equipotential for 1 volt. You cannot see anything, any pattern whatsoever, and there's a reason for that, okay? There is a reason for that, but very soon you're going to start to see a pattern there. You can see the y-axis goes from 0 to 4 centimeters, okay? Approximately 4 centimeters. And the x, that goes from approximately 1 centimeter to 2 centimeters. And now we are going to superimpose the data for 3 volts, say 1, 3, 5, 7, and 9, right? We're going to superimpose the data from 3 volts, and there is a little trick to do that. The way you do this, the way you do that is like that. You're going to click one of the data points, Okay, everything should be highlighted. Okay, right click, and then you're going to, let's see, add format data, select data. You're going to select data. Okay, here you go. And then this new window opens up. And what you are going to do you see we have the first series right in here? The first series is this point here for 1 vote. Okay, that was the first series. You might even want to, to add it there and label it 1 vote, like that. Okay, and now instead of series 1, you have 1 vote. And then you're going to add another series of data points. Okay, and you're going to give it a name 2 votes. No, it's not 2 votes, sorry, it's 3 votes. 3 votes. And what else you're going to do? You're gonna put the X values there. In order to put the X values there, all you have to do is to highlight this column where the X values show up, okay? And then you do the same for the Y, but first you gotta eliminate this equal 1. It's always, it's always there. And when you highlight the Y values, and look what we have another equipotential here. See the 1 volt equipotential here? And now this is the 3 volt equipotential here. Okay? It's not exactly in the vertical, it's bending a little bit, most likely because of the edge effect. And then you repeat for the other ones. Click, you gotta click OK first. Are you doing that? Are you doing that? Now you should have 2 equipotentials, 1 for 1 volt, the other one for 3 volts, okay? Then repeat for the other ones. Click, right click, select data, okay? And another one, and I'm gonna put here 5 volts, right? X data of 5 volts. Don't forget to get rid of this number 1. I don't have a clue why they keep on putting number 1s in there. And highlight for the Y. See, series X values, series Y values. So that was the little thing that I learned on my own. I discovered that on my own. I have never seen that posted in the internet. Click OK, and now we have our 3rd equipotential. You don't need to click OK. You don't need to click. I prefer that you don't click OK now, but just keep on adding series, okay? 1, 3, 5 volts. Add. Now we're gonna go for 7 volts. 7 volts, right? X value for 7 volts. Get rid of this equal 1, Y value for 7 volts. And then here you go, my other equipotential. Isn't that nice? If you have the data, typed there properly, you can plot the equipotentials with Excel. You can plot the equipotentials with Excel. And then finally, I'm going to click OK. I'm going to add my last equipotential, and then you go ahead and type 9 volts. X, highlight X. Y, get rid of your 1, your annoying 1, right? And you highlight it. Do you see that we have an outlier right in here? This point is clearly an outlier. Okay. This point, but you can also see that it's bending, right? Those are the so-called edge effect. This one is also bending a little bit. This one is bending a little bit. Okay. And those are your equipotentials. Everybody got? I want you all to do that. Okay. And let's see, I'm gonna go one by one to ensure that you folks have done. And it's 10:54, we have to go for our break very soon. Oh, there's something wrong here, let's see. Okay, I have to, that's okay, right? Okay, now I have to get out. I forgot to get out. Now let's go back to my spreadsheet. So plot. Okay, Jacqueline, did you manage to plot your graph there? I hate what, but I was wondering if you can show. Yeah, another example one more time. Okay, I'll help you out. Jacqueline managed to do that, right? Okay, and let's see. Jacqueline said she managed. I'll get to you. Okay, Vanessa, hang in there. You're good. Did you manage to do the plot? I can't hear from Yorgo. What happens?
Professor, he just messaged me saying that his internet went down.
Okay, so we're gonna put a star here. Thank you. And let's hope he can get back soon. Giselle, did you manage to plot it? Yes, okay, no problem. Okay, Paul Zapata, did you manage to plot it?
Yes.
Okay, so it was Vanessa Scalera. Okay, so I got to you now. Vanessa, let's do that again, huh? I'm back here, this one. Okay, I'm going to start from scratch, okay? Start from scratch. At this point in time, you already know how to plot a graph in Excel, right, Vanessa? Have you ever plotted a graph in Excel? If you know how to plot a graph in Excel, it's gonna be helpful for you. Otherwise, I just walk you step by step, okay? Hello, Vanessa, Vanessa Scalera. Just the last part. Let's do that. Let's do it step by step, okay? So go ahead, highlight X and Y. Okay, highlight X and Y for 1 volt. Are you done with that? Let me know when you have highlighted, and then you go for the, insert, chart, scatter, right? Now I want to make sure that you did that. Did you do that, Vanessa? It's just the last part that you do not know, right?
Yeah.
Okay. So now the next step. What's the next step? You have your graph, right? You have let's say your graph that you're going to keep on using. You want to, add points to this graph. So what do? You click one of the data points. Notice that all data points are highlighted, right? Right click, and then you select data. Okay? Select data. What happened here? The window didn't show up. Something happened. Let's try it again. Click one of the data point. Something happened here. Oh, that's because the window is the wrong side. Okay, here you go. You should see this window here. Okay, you should see this window. Okay, so what we are going to do? Let me close this window. I'm going to start all over again. Here you go. One data point. Right click that data point. Select data. Yeah. Okay, that's what we have. The first thing that you want to do here, you want to rename the series. Okay. You highlight series, add it, and you write down 1 volt. Okay. Note, see that X values, G9 to G14. That's what it is, right? X values is G9, right? To G14, right? And the Y value is what? H9 to H14, right? Click OK. And now you have your series of 1 volt. Add, right? Because we want to add the values, the data points for 3 volts. You name it, series name, 3 volts. Okay. X value, you highlight those cells along the X value. And get rid of this one here. Highlight those cells in the Y value. Click OK. Are you following now, Vanessa? Give some feedback.
Yeah, I got it. Already.
Yeah, good. And then you have to repeat for the other ones, right? Add 5 volts, X values. Get rid of this annoying number 1. You gotta tell Bill Gates to get rid of this one for us. Here you go, click OK, and so on, right? And let's see, let me finish 7 volts. 7 volts, X value, Y value, click OK, 9 volts, X value, Y value, and then we finally have, and then you can click OK, you have almost done, you're not completely done, there is a little bit more thing that you have to do, okay? But the secret was to plot those equipotentials. Okay, now let's go down the. So Vanessa, you already know how to do that, right, Vanessa? Vanessa Scalera. What about Norberto? Did you manage to do that, Norberto?
Yeah, I was able.
Okay, that's good. Next is Vanessa Mena, the other Vanessa.
Yeah, I was able to do it.
Okay, you managed to do all the how many? 5, right? 1, 3, 7, 9. 1, 3, 5, 7, 9. 5. Yeah, all the 5 equipotentials. Right? Let's go for
Yeah.
Sky. Okay, thank you. Sky, how did you manage to do that, Sky? All the 5 equipotentials?
Yes.
Okay, thank you. Ashley? Yes, good. Next is Corina. Yes, good. So we are advancing here. Okay, so let's go back to our graph. And now I want to make the graph to look better, okay? And let's not forget, right, I will get that PowerPoint presentation that I showed to you before. Let me get that. Let me see if I can find it. Add electric field, electric charge. It must be this one here, okay? Okay, remember I showed that to you last time. Resistivity paper. Resistivity paper is electrodes, right? Place resistivity paper on the top of a cork board, just like the guy did. You know, the 4 pins. Remember? He did exactly what I displayed that for you here. You know, and then he put the pins on each electrode, left electrode, right electrode. Power supply, he set the power supply to 6 volts. I set mine to 10. Okay, get black cable and connect one end of the black jack to of the power supply. One end of the get the black cable and connect one end to the black jack of the power supply and the other end to the electrode, the last electrode of the paper. Now the electrode is negatively charged. Then you repeat for the right electrode, but that you do that for the red cable and red jack of the power supply, and now you are positively charged. And then here you go, x-axis, okay? When I perform those experiments with my student, I ask them to put an x-axis right in the middle of the electrode. Here is going to be the origin of my x-axis, okay? Next is going to be the y-axis. So all those x and y coordinates that you see there in the spreadsheet is with respect to this x-y axis with respect to the electrode, okay? Next, here is the line where we have where the edge effects start to become important, right? And then, you know, we go ahead and do the measurements that we did. He go 1 volt here, 3 volt. We usually do like that. You know, first, I usually ask my students, first, let's get the data points along the x-axis, y equal to 0. That's what I ask my students to do. You know, identify 1 volt, 3 volts, 5 volts along this axis. And then, you know, we identify the points along this imaginary line at the edge of the electrodes. The procedure that I tell them to do. Okay, and then do for 1, 3, 5, 7, 9 volts. and then outside that region, so you can see the edge effects, okay? And then I usually like to get 6 data points for each potential, okay? And here you go, 6, 1, 2, 3, 4, 5, 6. That's what I usually do in my experiments. Not just the experiments at LA Harbor, but also professional experiments as well. Okay, so here you go. Here are the equipotential lines. That's what you must have right now. It's only the upper half. It's only the upper half because the lower half is just like a mirror image of what you see here. Okay? Just a mirror image of what you see. And now that we have our graph plotted, we are going to make it look nicer. Okay? We're gonna make it look nicer. Okay, note, see that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 2, 4, 6, 10 to minus 2, right? 8, 10, 10, 10. So we have to put some, what I want you to do, I want you to, instead of putting in this format, I don't like this format, exponential format, okay? The scientific notation, I don't like this format. I put it in regular number format. So you go ahead and you click right in here along this axis, the numbers along this axis, double click. Man, we are getting to our break already. Let's keep on going, let's keep on going. We need to move forward, right? When you double click here, this panel shows up. And then you go ahead, click on the number at the bottom. Instead of scientific, just put numeric format, okay? And now it shows up only the zeros. Shows up only the zeros because I don't have enough decimal places there. See, and the decimal place, the number of decimal places are dictated right in here in this box. If I put 1 decimal place only, I still don't have enough resolution of my axis, right? So what you have to do, you have to put a second decimal place. Don't put more than 2 decimal places. Okay, so from 0 to 9 centimeters, almost 10 centimeters. Okay, and then you repeat for this one. Okay, repeat for this one. Here you go. Let's see. Double click. Okay, go to the axis number. Okay. Instead of scientific, change to numeric format. Everything is 0, right? Everything is 0 because you do not have enough decimal places in there. If I put 1 decimal place, let's see what happens. 0, 0, 0, 0.1, 0.1, 0.1, right? So we still don't have enough decimal places. Let's put 2 decimal places. Here you go. 0, 2, 0, 4, 0, 6, 0, 8. Now we have enough decimal places here. We don't need more than that. Okay. Everybody did that? Adjust what I want you to do, right? Plot 2 graphs. Equipotential, let's see here. We're using, yeah. Plot 2 graphs, equipotential curves and lines, right? And okay, we didn't get to this one yet. We came to this one, okay? Adjust the X and Y numbers along the axis, okay? And to make it even nicer, and that I recommend you do the same, I think that those numbers are too small, okay? I think those numbers are too small. See, the size is 9. I don't like size 9. Let's use size 14, okay? In addition to size 14, boldface it to make it very visible, and repeat for this other one. Size 14, boldface, okay? So we labeled the axis. Now you have to put the label for those axes. Okay, one more. Am I going too fast? Okay, so let's go back here. Adjust equipotential, adjust the X and Y numbers along the axis. Let's see. Let's put it this way. Here you go. Axis. Here you go. Make, let's see. Bold face the numbers. Bold face the numbers. And use font size 14. Okay? And then what you're going to do next? Put the axis label. There's a way to do that too. Right in here. Here is going to be the X coordinate of your paper. This is going to be the Y coordinate of your paper. How do we do that? Click the graph. We need to put a label. We still don't have a label here describing what those two axes, right? So notice that when I click the, watch here at the top. When I click the graph, you know, you end up with a chart design and a format, right? I unclick, the chart design format disappear. Click again, chart design format. Click chart design, add chart element, axis title. Primary vertical, right? Axis title, primary horizontal. Oops, what happened? Something bad happened here. Let's try it again. Okay, axis title, primary horizontal. Okay, good. Like that. Very small, see? I don't want you to keep it small like that. You know, this one is 14. Axis title, make it 16, size 16. Also bold face it, so you can see them very nicely. I repeat for this one here, bold face, size 16, right? And then what do we do? X coordinate, right? X coordinate, you put that units in meter, okay? And then you repeat, here is gonna be Y coordinate, the unit between parentheses. 11, 12, I wanna take a break. Okay. Let's take a break. And we were, you know, in my classes, our priority is to plot the graph, okay? That's what the priorities are in my labs. Once we have the graph out of the way, then we do the other things. And hopefully we're gonna have enough time to do the rest of the thing. Any questions before we move forward? No questions? Okay, so plot two graphs. There will be two graphs. We're first plotting this first graph here. Put the axis labels, the labels of the axis, right? The labels of the axis. Axis must be AX, huh? Okay, like that. Use font size 16 and bold face it. Okay. And then I will, here you go. Break 11:15 a.m. to 11:30 a.m. Okay, so I see you in 15 minutes. Stop sharing and what else? Okay, I'm back here. Okay, so the graph is pretty good. Okay, that's what we want for the graph. And for most of you who is taking the course with me for the first time, right? What you're going to do next? Remember, I told you it's 2 graphs that you have to worry about. Okay, so the first graph is done. The second graph is going to be the V average versus X average. Okay, and the spreadsheet is already programmed properly for you, okay, to do that. Notice that we have V here, right? V here for 3 volts, V here for 5 volts, and so on, right? 7 and 9. And we have X here, right? X here. Okay, X here. Okay, and if we go back to my graph, you can see that the least amount of variation that you get between X and Y, it is the X that varies the least, right? Here the X varies the least because this, Y goes from 0 to...
Can you share your screen?
Oh, thank you. Yeah, thank you for telling me. Here you go. Here we have the graph, right? And we plot the first graph, okay? And now you want to plot the second graph, which is V average versus X average. Okay, why is X average, right? X average is the one that, the X is the one that varies the least, right? Y varies from 0 to 0.1, from 0 to 10 centimeters. But because we are talking about 2 parallel plates, 2 parallel charged plates, it's going to be the X that's going to vary the least. Because the equipotential are going to have almost the same X coordinate. Okay. Oh man. Thank you. So what are you doing? The spreadsheet has already been programmed to take the average of X for each of their respective equipotentials. Okay. So here you go. Average of those values for 1 volt. Average of those values for 3 volts, average of those values for 5 volts, and so on, right? 7 volts and 9 volts. And the average of V as well, because they're not going to be exactly 1. Okay, they're going to be a little bit off. Okay, average for V of all those V values, average for all those other V values, and so on, right? See the highlight here, the highlight right here. And now you should plot it. V and X, V average and X average. When you plot V and X average, you should get exactly what I told you before, right? You should get a linear relationship between the potential and the X because this is a uniform electric field. Let's plot it. Insert chart, here you go, see? And then, you know, you're going to, what you're going to do next, you're going to, in this case, you're going to add a trend line, just like we have been doing since physics 6, right? For those who didn't take the course with me, it's not difficult to add a trend line. You click on the data points, right click, add trend line, right? And then you display equation on chart and R square on chart. Right in here. See this value here that you see here? This value that you see right in here is the value of the electric field. Is the value of the electric field. The Y that you see here should be voltage. Okay. Oh, no. Here you go. Y is actually the voltage, right? So I'm going, why is it doing that? Huh, strange. Let's see what's going on here. Let's see if I can get, you keep on, oh man, that's so lousy. Okay, so I'm gonna leave this way. I try to edit the Y, I cannot. Okay, it's supposed to let me edit, but it doesn't let me. But here should be voltage, electric field times X plus initial voltage. Because those are statistic type of measurements. Ideally, this value should be 0. But because this is real life, right? Because this not just is real life, but because we also have so those edge effects, we're getting this small intercept here of 0.598. And don't forget that we still have this outlier. So those are the two graphs that you're supposed to plot. 1140, 1138, right? And then go ahead and, change the format of the numbers here. Okay, don't keep scientific format, keep it numeric format. Okay, so let's do that again. Okay, click on the numbers along the x-axis. When you click the numbers along the x-axis, this panel shows up with all those options, right? See, we can even retract axis options, right? Tick marks, we can retract. Labels, we can retract. But what we want to change is the numbers. We want change from scientific to numeric. And then we're going to add decimal places, right? I believe it's 2 decimal places. Yeah, 2 decimal places is a good one. 2 centimeters, 4 centimeters, 6 centimeters, and so on, right? And you do the same thing here. You do not need the scientific format. You can use numeric format. Numeric format is preferable to scientific. And just put 1 decimal place. We don't need more than 1 decimal place. Okay? And then you go ahead and do the same thing that we did before. Right? Highlight those, bold face it, make sure you make it nice. 12, is that 12? No, 14. We should use 14. Here is bold face 14. And then you add what else? You add the chart element, axis title, primary horizontal, and primary vertical. Okay, primary horizontal, you want to do that, what, 16? And bold face, this one is what, 14? I believe it was 14, right? Yeah, that's 14, this one can be 16. And then you go ahead, you put XAVG between parentheses in meter, right? But AVG should be subscript. So what do we do? 1, 2, 3, and highlight it, right click, font, and subscript, right? If you want to make it fancy, italicize to make it look nice, right? And you do the same here for the V. VAVG between parentheses, voltage. And then you increase the font size and boldface it. The 16 or 18? 16, right? 16. And the AVG, you font subscript, make it look nice. Okay. So we did the graphs. Any questions so far? Let's see if anybody's. Okay, so going back to my notes, right? So what did you do? Let's see. So plot one, plot graph one, plot graph two, right? What you're going to do next, add the units to the tables. Okay. Add units to the tables. Adjust the significant figures on the table, on the tables, right? And I'm going to show you how to do that. Okay, so here you have to put your units. Make sure you fill it up, okay? Put your units here too as well. The sigma that you see, there is a name for the sigma. The sigma is called the standard deviation. Okay. Sigma is standard deviation. Sigma x is standard deviation from the mean. Also known as the error. Is less than the standard deviation, is less than the standard deviation, less than, and so on. Okay. And then just the ratio of this one by the average. Okay, the standard deviation of the mean is, just 2% of the average on the order of, let's see, here is 1%, 2%, 5%, less than 1% and 2%, very low. When you have those low values, on the order of less than 5%, it means that you have very good data. Okay. What else you have to do? You plot the tables, right? Let's see. Wait a minute. Let's organize that better, right? Instead of after plotting graph number 2, fill up table, third table. Third table is what? Table 1-3. Fill table 1-3. 1-3. Fill what you can. Oh, you know what? No, this one is the last thing you want to do. Let's go. That's the last thing, one of the last things you want to do. Okay, let's do it this way. Here you go. This one. What you want to do is 1.4. Yeah, you want to write that down 50. Okay, 50 value. This low value is 50. Okay, 50.008, which is the strength of the electric field, joules per coulomb. And then you gotta put the unit as well. Not joules per coulomb, sorry, it's volts per coulomb. Volts per, no, wait a minute, volts per centimeter, volts per meter. Okay, we can write that down here. Let's go. 50, I wanna copy this guy so we can study this equation, right? No, I didn't copy, what a shame. Okay, so the slope is 50 plus times, let me copy and paste. Here you go, like that. V average, right? V average is 50. I should not know what the unit is, okay? Let's just write down the way it is. 50 times x plus that is small 0.59, right? 0.59. Yeah, 0.5984. In my case, it's 0.5984. In your case, it should be different. Oh, okay. Now we are going to look at, don't forget, this term that you see here is the electric field. Okay, because the voltage is directly proportional to the electric field times the x. Because this is supposed to be a voltage, This guy here, that's Lon, is also has unit of voltage. Okay, so what you see here is actually 0.5984 volts. And since your X has an implicit unit of meter, what you have right in here should have a unit of volt divided by meter. Just do your, what we call the dimensional analysis, okay? Volts per meter. So when I substitute here 1 centimeter, right, 0.01 meter, those two things cancel out, and the average voltage is going to be, 50.008 plus whatever you have here. Okay. And this guy here is your electric field. And now you can put the unit, not just the unit of the slope, but the unit of your electric field as well. Okay, here's going to be 50.00. So with this simple experiment, we can find out what's going to be the voltage. That should be 50.008. The electric field of your charge distribution, 1148. Okay, and now you can start working on that, okay? Volt, meter, meter, volt, meter, meter. All you gotta do here, copy and paste, that's all. Okay? Make sure you put it there. Otherwise, I want to take out points from you, okay? Here, you gotta look at the units of the X average. Okay? The units of X average is going to be meter. No, here too, the units of the V average is gonna be V, capital V, voltage. And now the tricky is this one here. This one is the tricky one, okay? It is the standard deviation. This one is also tricky, and this one is gonna be tricky as well. Remember, I'm doing that only this time, right? Next time, I'm not gonna do that. Telling what the units are, right? So let's take a look at the equation for the standard deviation. This is an equation that you must have by heart, but the same token that you are at this point in time, you already have the equation for average, right? That's the relationship between electric field and voltage, electric potential. There's a minus sign here, delta V over delta X. Plot the graph, find the slope, working the units, report them the main units of SI, working the significance field. Okay, here you go. This is the equation for the standard deviation. Okay? The standard deviation equation is going to be the sum of the sum of the difference of these differences here squared. Okay? So here in this case, it's going to be X value, first X value minus the X average is square. The second X value minus the average is square, plus the last, the difference between every X value with respect to average squared divided by N. Okay, that's how we define the standard deviation. See that? Summation, and then you take the square root. And now you have to do a dimensional analysis of this equation. And you tell me what's going to be the unit of sigma, of the standard deviation. Okay? This term here is going to be meter squared. This term here is going to be meter squared. This term here is going to be meter squared. So upstairs, I know that I have meter squared. Downstairs, just a regular number. It's just a regular number that with no unit whatsoever. Consequently, since we have to take the square root of everything that is square and meter square, the unit of sigma is going to be meter. Okay. Sigma x, the definition of sigma x is the standard deviation divided by the square root of number of points. This guy has no unit. Sigma has unit of meter, so you know that the unit also sigma x is going to be meter as well, okay? And finally, you have that other parameter. Let me, that you need to find the unit as well, sigma x over x average, right? Like that. Remember that? That's the other unit that you have to figure out. And it's not difficult, provided you do the dimensional analysis. You already know that sigma x, the unit of sigma x, okay? Square bracket, right? Square bracket stands for units, you know. Square bracket upstairs divide to square bracket downstairs. That's how you process this. Square bracket of sigma x is going to be meter. Square bracket of x average. What's the unit of x average? It's meter too, right? And you end up with a unit of 1. Okay, unit of 1 means that the quantity is unitless. Okay. So when you report the unit here of this ratio, you're going to report the unit 1. Okay, it's going to be meter, and unit 1. I'm going to erase it. Okay. Unit 1 means the quantity is unitless. 11:54. We have 6 more minutes to go. Okay, let's see. So we did this one here. I have to erase that so it doesn't carry over to the next time. And let me erase that as well. Okay. And then, you know, this part is easy, right? This part is number of data points is 6. 6, no, it's 5, sorry. 1, 2, 3, 4, 5. Okay. 1, 3, 5, 7, 9 is 5 data points. The average is whatever we got with that equation. R squared is whatever we got there as well, right? You saw that. This one is a little bit more difficult. This one I'm gonna cover with you next time, okay? Any questions? 11:55. So we're not done with this lab report yet. Next time we meet, I will show you how to do the rest. So there is no lab report due yet. Okay? But let's see how you're doing that. Oh, yeah, I still have to tell you about the significant digits, right? Next time I'll cover the significant digits as well. We didn't have enough time to do that now. So let's write that down here. Next time, next time we will cover the significant digits, and the confidence level, okay? Confidence level is a very important statistical parameter, statistical idea that people hasn't talked much about it, okay? And that's why I want you to be exposed to it. Okay, let's see how you're all doing there. 11:57. Now, Jacqueline, did you plot both graphs? Yes, you did. Okay, any questions? Plot graphs, fill up the units. And next time we'll talk about the other two things, that is confidence level and significant digits. Let's see, Yorgo. Is Yorgo back? Let's see. Yorgo, I don't see Yorgo here, right? We have 8 students now. Lizelle, are you there, Lizelle? I don't see Lizelle either. Let's put it here. Star Paul Zapata.
Yes.
Okay, do you have any questions, Paul?
No, I don't. Thank you, Professor.
Okay, let's go. Next one is Vanessa Escalera.
I'm good with the graphs.
Okay, anything else? Do you have any other question? Units, no problem?
No.
Okay, so we continue that next time. Norberto?
Yeah, I was able to plot the graph.
Okay, good. Any questions? Do you have any doubts?
No.
Okay, so next is Vanessa Mena.
I got all my graphs down.
You got, okay, that's good. Sky, did you get all your graphs?
I did all the graphs and I have no questions.
Okay, good. Next is Ashley. Hello, Ashley, are you there? Okay, let's put a star here on Ashley. Next is Corina. Did you plot your graphs, Corina?
Yes, I did.
Yeah, okay.
Yeah.
Okay, so we can stop now and I'll see you again next week. Right? So I see you then.
Thank you, Professor.
Welcome.